A heat pump is a device that provides heat energy from a source of heat to a destination called a heat sink. Heat pumps are designed to move thermal energy opposite to the direction of spontaneous heat flow by absorbing heat from a cold space and releasing it to a warmer one. A heat pump uses some amount of external power to accomplish the work of transferring energy from the heat source to the heat sink. While air conditioners and freezers are familiar examples of heat pumps, the term heat pump is more general and applies to many HVAC devices used for space heating or space cooling. When a heat pump is used for heating, it employs the same basic refrigeration-type cycle used by an air conditioner or a refrigerator, but in the opposite direction, releasing heat into the air-conditioned space rather than the surrounding environment. In this use, heat pumps generally draw heat from the cooler external air or from the ground. Overview. In heating, ventilation and air conditioning applications, the term heat pump usually refers to easily reversible vapor compression refrigeration devices optimized for high efficiency in both directions of thermal energy transfer. Heat spontaneously flows from warmer places to colder spaces. A heat pump can absorb heat from a cold space and release it to a warmer one. Heat is not conserved in this process, which requires some amount of external high-grade energy, such as electricity. Heat pumps are used to provide heating because less high-grade energy is required for their operation than appears in the released heat. Most of the energy for heating comes from the external environment, and only a fraction comes from electricity. In electrically powered heat pumps, the heat transferred can be 3 or 4 times larger than the electrical power consumed, giving the system a coefficient of performance of 3 or 4, as opposed to a COP of 1 of a conventional electrical resistance heater, in which all heat is produced from input's electrical energy. Heat pumps use a refrigerant as an intermediate fluid to absorb heat where it vaporizes, in the evaporator, and then to release heat where the refrigerant condenses, in the condenser. The refrigerant flows through insulated pipes between the evaporator and the condenser, allowing for efficient thermal energy transfer at relatively long distances. Reversible heat pumps. Reversible heat pumps work in either thermal direction to provide heating or cooling to the internal space. They employ a reversing valve to reverse the flow of refrigerant from the compressor through the condenser and evaporation coils. In heating mode, the outdoor coil is an evaporator, while the indoor is a condenser. The refrigerant flowing from the evaporator carries the thermal energy from outside air indoors, after the fluid's temperature has been augmented by compressing it. The indoor coil then transfers thermal energy to the indoor air, which is then moved around the inside of the building by an air handler. Alternatively, thermal energy is transferred to water, which is then used to heat the building via radiators or underfloor heating. The heated water may also be used for domestic hot water consumption. The refrigerant is then allowed to expand, cool, and absorb heat to reheat to the outdoor temperature in the outside evaporator, and the cycle repeats. This is a standard refrigeration cycle, save that the cold side of the refrigerator is positioned so it is outdoors where the environment is colder. In cooling mode the cycle is similar, but the outdoor coil is now the condenser and the indoor coil is the evaporator. This is the familiar mode in which air conditioners operate. Operating principles. Mechanical heat pumps exploit the physical properties of a volatile evaporating and condensing fluid known as a refrigerant. The heat pump compresses the refrigerant to make it hotter on the side to be warmed, and releases the pressure at the side where heat is absorbed. The working fluid, in its gaseous state, is pressurized and circulated through the system by a compressor. On the discharge side of the compressor, now hot and highly pressurized vapor is cooled in a heat exchanger, called a condenser, until it condenses into a high-pressure, moderate-temperature liquid. The condensed refrigerant then passes through a pressure-lowering device also called a metering device. This may be an expansion valve, capillary tube, or possibly a work-extracting device such as a turbine. The low-pressure liquid refrigerant then enters another heat exchanger, the evaporator, in which the fluid absorbs heat and boils. The refrigerant then returns to the compressor and the cycle is repeated. It is essential that the refrigerant reaches a sufficiently high temperature, when compressed, to release heat through the hot heat exchanger. Similarly, the fluid must reach a sufficiently low temperature when allowed to expand, or else heat cannot flow from the ambient cold region into the fluid in the cold heat exchanger. In particular, the pressure difference must be great enough for the fluid to condense at the hot side and still evaporate in the lower pressure region at the cold side. The greater the temperature difference, the greater the required pressure difference, and consequently the more energy needed to compress the fluid. Thus, as with all heat pumps, the coefficient of performance decreases with increasing temperature difference. Insulation is used to reduce the work and energy required to achieve a low enough temperature in the space to be cooled. To operate in different temperature conditions, different refrigerants are available. Refrigerators, air conditioners, and some heating systems are common applications that use this technology. Heat transport. Heat is typically transported through engineered heating or cooling systems by using a flowing gas or liquid. Air is sometimes used, but quickly becomes impractical under many circumstances because it requires large ducts to transfer relatively small amounts of heat. In systems using refrigerant, this working fluid can also be used to transport heat a considerable distance, though this can become impractical because of increased risk of expensive refrigerant leakage. When large amounts of heat are to be transported, water is typically used, often supplemented with antifreeze, corrosion inhibitors, and other additives. Heat sources. Sinks. A common source or sink for heat in smaller installations is the outside air, as used by an air source heat pump. A fan is needed to improve heat exchange efficiency. Larger installations handling more heat, or in tight physical spaces, often use water source heat pumps. The heat is sourced or ejected in water flow, which can carry much larger amounts of heat through a given pipe or duct cross-section than airflow can carry. The water may be heated at a remote location by boilers, solar energy, or other means. Alternatively, when needed, the water may be cooled by using a cooling tower, or discharged into a large body of water, such as a lake or stream. Geothermal heat pumps or ground source heat pumps use shallow underground heat exchangers as a heat source or sink, and water as the heat transport medium. This is possible because below ground level, the temperature is relatively constant across the seasons, and the earth can provide or absorb a large amount of heat. Ground source heat pumps work in the same way as air source heat pumps, but exchange heat with the ground via water pumped through pipes in the ground. Ground source heat pumps are more simple and therefore more reliable than air source heat pumps as they do not need fan or defrosting systems and can be housed inside. Although a ground heat exchanger requires a higher initial capital cost, the annual running costs are lower, because well-designed ground source heat pump systems operate more efficiently. Heat pump installations may be installed alongside an auxiliary conventional heat source such as electrical resistance heaters, or oil or gas combustion. The auxiliary source is installed to meet peak heating loads, or to provide a backup system. Applications. HVAC. In HVAC applications, a heat pump is typically a vapor compression refrigeration device that includes a reversing valve and optimized heat exchangers so that the direction of heat flow may be reversed. The reversing valve switches the direction of refrigerant through the cycle and therefore the heat pump may deliver either heating or cooling to a building. In cooler climates, the default setting of the reversing valve is heating. The default setting in warmer climates is cooling. Because the two heat exchangers, the condenser and evaporator, must swap functions, they are optimized to perform adequately in both modes. Therefore, the efficiency of a reversible heat pump is typically slightly less than two separately optimized machines. Plumbing. In plumbing applications, a heat pump is sometimes used to heat or preheat water for swimming pools or domestic water heaters. The heat energy removed from an air-conditioned space may be recovered for water heating. Refrigerants. Until the 1990s, the refrigerants were often chlorofluorocarbons such as A12, one in a class of several refrigerants using the brand name Freon, a trademark of DuPont. Its manufacture was discontinued in 1995 because of the damage that CFCs caused to the ozone layer if released into the atmosphere. One widely adopted replacement refrigerant is the hydrofluorocarbon known as A134A. Heat pumps using a 134A are not as efficient as those using a 12 that they replace, and therefore, more energy is required to operate systems utilizing a 134A than those using a 12. Other substances such as liquid R717 ammonia are widely used in large-scale systems, or occasionally the less corrosive but more flammable propane or butane can also be used. Since 2001, carbon dioxide, R744, has increasingly been used, utilizing the transcritical cycle, although it requires much higher working pressures. In residential and commercial applications, the hydrochlorofluorocarbon R22 is still widely used. However, HFCr 410A does not deplete the ozone layer and is being used more frequently. Hydrogen, helium, nitrogen, or plain air is used in the Stirling cycle, providing the maximum number of options in environmentally friendly gases. More recent refrigerators use a 600A, which is isobutane, and does not deplete the ozone and is friendly to the environment. Dimethyl ether is also gaining popularity as a refrigerant. Efficiency. When comparing the performance of heat pumps, it is best to avoid the word efficiency, which is a very specific thermodynamic definition. The term coefficient of performance is used to describe the ratio of useful heat movement per work input. Most vapor compression heat pumps use electrically powered motors for their work input. However, in many vehicle applications, mechanical energy from an internal combustion engine provides the needed work. According to the US EPA, geothermal heat pumps can reduce energy consumption up to 44% compared with air source heat pumps and up to 72% compared with electric resistance heating. When used for heating a building with an outside temperature of, for example, 10 degrees Celsius, a typical air source heat pump has a COP of 3 to 4, whereas an electrical resistance heater has a COP of 1.0. That is, 1 joule of electrical energy will cause a resistance heater to produce only 1 joule of useful heat, while under ideal conditions, 1 joule of electrical energy can cause a heat pump to move 3 or 4 joules of heat from a cooler place to a warmer place. Note that an air source heat pump is more efficient in hotter climates than cooler ones, so when the weather is much warmer the unit will perform with a higher COP. Conversely, in extreme cold weather the COP approaches 1. Thus when there is a wide temperature differential between the hot and cold reservoirs, the COP is lower. On the other hand, ground source heat pumps benefit from the moderated temperature underground, as the ground acts naturally as a store of thermal energy. Their year-round COP is therefore normally in the range of 2.5 to 5.0. When there is a high temperature differential, it takes more work to move the same amount of heat to indoors than on a milder day. Ultimately, due to Carnot efficiency limits, the heat pump's performance will approach 1.0 as the outdoor to indoor temperature difference increases for colder climates. This typically occurs around 18 degrees Celsius outdoor temperature for air source heat pumps. Also, as the heat pump takes heat out of the air, some moisture in the outdoor air may condense and possibly freeze on the outdoor heat exchanger. The system must periodically melt this ice. When it is extremely cold outside, it is simpler, and wears the machine less, to heat using an electric resistance heater rather than to overload an air source heat pump. The design of the evaporator and condenser heat exchangers is also very important to the overall efficiency of the heat pump. The heat exchange surface areas and the corresponding temperature differential directly affect the operating pressures and hence the work the compressor has to do in order to provide the same heating or cooling effect. Generally, the larger the heat exchanger the lower the temperature differential and the more efficient the system becomes. Heat exchangers are expensive, requiring drilling for some heat pump types or large spaces to be efficient, and the heat pump industry generally competes on price rather than efficiency. Heat pumps are already at a price disadvantage when it comes to initial investment compared to conventional heating solutions like boilers, so the drive towards more efficient heat pumps and air conditioners is often led by legislative measures on minimum efficiency standards. In cooling mode, a heat pump's operating performance is described in the US as its energy efficiency ratio or seasonal energy efficiency ratio, and both measures have units of British thermal unit/HRW, A equals 0.293 watts per watt. A larger ER number indicates better performance. The manufacturer's literature should provide both a COP to describe performance in heating mode, and an ER or CR to describe performance in cooling mode. Actual performance varies, however, and depends on many factors such as installation, temperature differences, site elevation, and maintenance. Heat pumps are more effective for heating than for cooling an interior space if the temperature differential is held equal. This is because the compressor's input energy is also converted to useful heat when in heating mode, and is discharged along with the transported heat via the condenser to the interior space. But for cooling, the condenser is normally outdoors, and the compressor's dissipated work must also be transported to outdoors using more input energy, rather than being put to a useful purpose. For the same reason, opening a food refrigerator or freezer actually heats up the room rather than cooling it because its refrigeration cycle rejects heat to the indoor air. This heat includes the compressor's dissipated work as well as the heat removed from the inside of the appliance. The COP for a heat pump in a heating or cooling application, with steady-state operation, is where is the amount of heat extracted from a cold reservoir at temperature, is the amount of heat delivered to a hot reservoir at temperature, is the compressor's dissipated work. All temperatures are absolute temperatures usually measured in kelvins or degrees Rankine. Coefficient of performance and lift, the COP increases as the temperature difference, or lift, decreases between heat source and destination. The COP can be maximized at design time by choosing a heating system requiring only a low final water temperature, and by choosing a heat source with a high average temperature. Domestic hot water and conventional heating radiators require high water temperatures, reducing the COP that can be attained, and affecting the choice of heat pump technology. One observation is that while current best practice heat pumps have a typical COP around 4, no better than 5, the maximum achievable is 8.8 because of fundamental Carnot cycle limits. This means that in the coming decades, the energy efficiency of top-end heat pumps could at least double. Cranking up efficiency requires the development of a better gas compressor, fitting HVAC machines with larger heat exchangers with slower gas flows, and solving internal lubrication problems resulting from slower gas flow. Depending on the working fluid, the expansion stage can be important also. Work done by the expanding fluid cools it and is available to replace some of the input power. Types, compression versus absorption. The two main types of heat pumps are compression and absorption. Compression heat pumps operate on mechanical energy, while absorption heat pumps may also run on heat as an energy source. An absorption heat pump may be fueled by natural gas or LP gas, for example. While the gas utilization efficiency in such a device, which is the ratio of the energy supplied to the energy consumed, may average only 1.5, that is better than a natural gas or LP gas furnace, which can only approach 1. Heat sources and sinks. By definition, all heat sources for a heat pump must be colder in temperature than the space to be heated. Most commonly, heat pumps draw heat from the air or from the ground. The heat drawn from ground-sourced systems is in most cases stored solar heat, and it should not be confused with direct geothermal heating, though the latter will contribute in some small measure to all heat in the ground. True geothermal heat, when used for heating, requires a circulation pump but no heat pump, since for this technology the ground temperature is higher than that of the space that is to be heated, so the technology relies only upon simple heat convection. Other heat sources for heat pumps include water. Nearby streams and other natural water bodies have been used, and sometimes domestic wastewater which is often warmer than cold winter ambient temperatures. A number of sources have been used for the heat source for heating private and communal buildings. Air source heat pump, air heat pump, air water heat pump. Air heat pumps, that extract heat from outside air and transfer this heat to inside air, are the most common type of heat pumps and the cheapest. These are similar to air conditioners operating in reverse. Air-water heat pumps are otherwise similar to air heat pumps, but they transfer the extracted heat into a water heating circuit, floor heating being the most efficient, and they can also transfer heat into a domestic hot water tank for use in showers and hot water taps of the building. However, groundwater heat pumps are more efficient than air-water heat pumps, and therefore they are often the better choice for providing heat for the floor heating and domestic hot water systems. Air source heat pumps are relatively easy and inexpensive to install and have therefore historically been the most widely used heat pump type. However, they suffer limitations due to their use of the outside air as a heat source. The higher temperature differential during periods of extreme cold leads to declining efficiency. In mild weather, COP may be around 4.0, while at temperatures below around 0 degrees Celsius an air source heat pump may still achieve a COP of 2.5. The average COP over seasonal variation is typically 2.5-2.8, with exceptional models able to exceed this in mild climates. In areas where only fossil fuels are available, air source heat pumps would be used as an alternative, supplemental heat source to reduce a building's dependence on fossil fuel. Depending on fuel and electricity prices, using the heat pump for heating may be less expensive than using fossil fuel. A backup fossil fuel, solar hot water or biomass heat source may still be required for the coldest days. The heating output of low-temperature optimized heat pumps still declines dramatically as the temperature drops, but the threshold at which the decline starts is lower than conventional pumps, as shown in the following table. Ground source heat pump, ground a heat pump, soil a heat pump, rock a heat pump, water a heat pump. Ground a water heat pump, soil a water heat pump, rock a water heat pump, water a water heat pump. Ground source heat pumps, also called geothermal heat pumps, typically have higher efficiencies than air source heat pumps. This is because they draw heat from the ground or groundwater, which is at a relatively constant temperature all year round below a depth of about 30 feet. This means that the temperature differential is lower, leading to higher efficiency. Well-maintained ground source heat pumps typically have COPs of 4.0 at the beginning of the heating season, with lower seasonal COPs of around 3.0 as heat is drawn from the ground. The trade-off for this improved performance is that a ground source heat pump is more expensive to install, due to the need for the drilling of boreholes for vertical placement of heat exchanger piping or the digging of trenches for horizontal placement of the piping that carries the heat exchange fluid. When compared, groundwater heat pumps are generally more efficient than heat pumps using heat from the soil. Closed-loop soil or ground heat exchangers tend to accumulate cold if the ground loop is undersized. This can be a significant problem if nearby groundwater is stagnant or the soil lacks thermal conductivity, and the overall system has been designed to be just big enough to handle a typical worst-case cold spell, or is simply undersized for the load. One way to fix cold accumulation in the ground heat exchanger loop is to use groundwater to cool the floors of the building on hot days, thereby transferring heat from the dwelling into the ground loop. There are several other methods for replenishing a low-temperature ground loop. One way is to make large solar collectors, for instance by putting plastic pipes just under the roof, or by putting coils of black polyethylene pipes under glass on the roof, or by piping the tarmac of the parking lot. Exhaust air heat pump, exhaust air heat pump, exhaust air water heat pump. Water source heat pumps, uses flowing water as source or sink for heat, single pass versus recirculation, single pass a water source a body of water or a stream, recirculation, when cooling, closed loop heat transfer medium to central cooling tower or chiller, when heating, closed-loop heat transfer medium from central boilers generating heat from combustion or other sources. Hybrid heat pumps, when outdoor air is above 4 to 8 Celsius, they use air. When air is colder, they use the ground source. These twin-source systems can also store summer heat, by running ground source water through the air exchanger or through the building heater exchanger, even when the heat pump itself is not running. This has dual advantage: it functions as a low running cost for air cooling, and it cranks up the temperature of the ground source, which improves the energy efficiency of the heat pump system by roughly 4% for each degree in temperature rise of the ground source. Air-water heat pump. The air-water heat pump is a hybrid heat pump, developed in Rostock, Germany, that uses only renewable energy sources. Unlike other hybrid systems, which usually combine both conventional and renewable energy sources, it combines air and geothermal heat in one compact device. The air-water heat pump has two evaporators, an outside air evaporator and a brine evaporator, both connected to the heat pump cycle. This allows use of the most economical heating source for the current external conditions. The unit automatically selects the most efficient operating mode, air or geothermal heat, or both together. The process is controlled by a control unit, which processes the large amounts of data delivered by the complex heating system. The control unit comprises two controllers, one for the air heat cycle and one for the geothermal circulation, in one device. All components communicate over a common bus to ensure they interact to enhance the efficiency of the hybrid heating system. The German Patent and Trademark Office in Munich granted the air-water heat pump a patent in 2008, under the title OE heat pump and method for controlling the source inlet temperature to the heat pump This hybrid heat pump can be combined with a solar thermal system or with an ice storage. It trades and is marketed under the name ThermSelect. In the United Kingdom, ThermSelect won the 2013 Commercial Heating Product of the Year award of the HVR Awards for Excellence, organized by Heating and Ventilating Review, an industry magazine. Heat distribution. Heat pumps are only highly efficient when they generate heat at a low temperature differential, ideally around or below 32 degrees Celsius. Normal steel plate radiators are not practical, because they would need to be 4 to 6 times their current size. Underfloor heating is one ideal solution. When wooden floors or carpets would spoil efficiency, wall heaters and piped ceilings can be used. These systems have the disadvantage that they are slow starters, and that they would require extensive renovation in existing buildings. The alternative is a warm air system. Such a setup can either complement slower floor heating during warm-up, or it can be a quick and economical way to implement a heat pump system into existing buildings. Oversizing the fans and ductwork can reduce the acoustic noise they produce. To efficiently distribute warm water or air from a heat pump, water pipes or air shafts must have significantly larger diameters than in conventional, hotter source systems, and underfloor heaters should have much more pipes per square meter. Solid-state heat pumps, magnetic. In 1881, the German physicist Emil Warburg put a block of iron into a strong magnetic field and found that it increased very slightly in temperature. Some commercial ventures to implement this technology are underway, claiming to cut energy consumption by 40% compared to current domestic refrigerators. The process works as follows: powdered gadolinium is moved into a magnetic field, heating the material by 2 to 5 degrees Celsius. The heat is removed by a circulating fluid. The material is then moved out of the magnetic field, reducing its temperature below its starting temperature. Thermoelectric. Solid-state heat pumps using the thermoelectric effect have improved over time to the point where they are useful for certain refrigeration tasks. Thermoelectric heat pumps are generally only around 10 to 15% as efficient as the ideal refrigerator, compared with 40–60% achieved by conventional compression cycle systems. However, this area of technology is currently the subject of active research in materials science. Thermoacoustic. Near-solid-state heat pumps using thermoacoustics are commonly used in cryogenic laboratories. Historical development, milestones. 1748 William Cullen demonstrates artificial refrigeration. 1834, Jacob Perkins builds a practical refrigerator with diethyl ether. 1852, Lord Kelvin describes the theory underlying heat pump. 1857, Peter von Rittinger develops and builds the first heat pump. 1940, Robert C. Weber is credited as developing and building the first ground heat pump. See also. References. External links. Heat pump at Encyclopaedia Britannica, practical information on setting up geothermal heat pump systems at home, pictures on private communal heat pump installations, International Energy Agency heat pump program, information site for heat pumping technology.